Okay. Good morning, good evening, everyone, depending on wherever you are calling from in the world or listening to this as a recording. This is weekly science review number 4, organized by Vetri Labs. We here at Vetri Labs focus on enabling electrochemical technologies and the implementation of them at scale. Today's topic is going to be on gold recycling. So without much ado, let's start that. So as you know, this session is being recorded. We can turn the video off during the recording session, and then after that, during the discussion session, we can come back on the video. So I'll start with that first. Can everyone see the screen and hear me well?
Yes, yes.
Thank you. So as I mentioned earlier, today's topic is on gold recycling. And this is a novel approach that this team came up with, the Chi and team from, I think we're based in Japan. The background is that as we come up with more and more electronic articles, there's lots of printed circuit boards. And due to the unique nature of inert nature of gold and the electrical conductivity being very good, there's lots of gold that's being used as part of the circuit. Over a period of time, the amount of gold that's used in these printed circuit boards came down. But even today, the concentration of gold in these printed circuit boards is in the range of 40 to 400 ppm by mass. Just as a comparison, this is over 10 times that of what's available in the highest grade ore. So there is still value in extracting gold out of these. There's sustainability, there's also economic impetus to do this. And with that, we can get a lot of pure gold by extracting gold out of these. What's the current process? Waste PCBs, WPCBs, you take that and then you dismantle it, pulverize it, making it into powders. And you go through a physical separation. This is where the metallic and the plastic components are being separated using different techniques, magnetic, electrostatic, eddy current, etc. And then you melt it completely through the pyrometallurgy process. You melt this, and then you separate through electrometallurgy, through application of electric field, you separate the metals. Even with that separation, it's not fully uniquely separate, meaning there'll be mixture of components. And then you go through this hydrometallurgy process where you do a lot of complexation and oxidizing strong solvents as part of this hydrometallurgy. And then you go through sediment separation, solvent extraction, reduction, and then finally gold is extracted out of this. Okay, as you can see, the drawbacks because of the beneficial nature of gold being inert chemically also poses a challenge when you're trying to recycle it, right? On the one hand, it helps us reduce the corrosion and be inert, but at the same time, when we want it to react, it doesn't react as well. So we have to use strong complexing agents and oxidizing agents. The examples of some of these solvents, these are like cyanide and hydrogen peroxide, hydrochloric acid and chlorine, mixture of hydrochloric acid and nitric acid, or mixture of hydrochloric acid and hydrogen peroxide. These are all strong oxidizing agents, and as a result, this leads to hazardous liquid waste coming out of this hydrometallurgy process. In addition, because of the fact that it's not selective enough, you have to do multiple steps to separate the various constituents. So that also adds time to this process. So the novel approach that this team came up with is where you start with this W waste PCBs, you go through the powdering, pulverization, physical separation. Then they start with alloying with a component. Here they refer to as R. In this particular example that they're using sodium. So alloy with another element R, and then dissolve that alloy in a molten salt solution, and then you electrolyze it. In this case, it's an anodic deposition. So oxidizing and then depositing. Typically, all of the electrochemical deposition happens on the cathode, where you start with the cationic component, Na plus, H plus, all of these are depositions, right? Copper, all of these electroplating, chromium, copper, all of them start as a cation and then deposit on the cathode. Whereas in this case, they're using gold as an anionic, not cationic, and then lose electrons and then deposit on the anode. So that's the method that they have proposed. This R is depositing that we started with, deposits on the cathode can be recycled. So that's the approach that they've come up with. In terms of the electrolysis, this is the schematic. Essentially, you start with this alloy, which has this R component as a cation, and then Mn minus, which is the anion. In this case, it's gold. You start with that, and then you deposit the R on the cathode, and then gold, or in this case, generalized as Mn minus, deposited on the anode. So there's no side reactions of chlorine gas evolution, and then there is a reusability of this R, as we saw earlier. When you look at the time and the process flow, this is a good comparison that they've enumerated in the paper. Here's your neutral valency. This is metallic. So in the traditional process, you dissolve it, all of the metals, and then initial dissolution, and then the dissolution in acid. It takes a long time, and then you separate it. When you dissolve and then do all of this, it's in the cationic form. So you started with the metal, and then you went to the cationic form, and then you reduce it to deposit as a metal again. So that's the path. In this proposed approach, alloying, it goes as an anion, and then you oxidize it and then come back. So overall, it's a simple operation, shorter time, zero consumption of reactants, no hazardous waste. So the specifics of the experimental setup and the process, they're using argon gas as an inert gas here. They use sodium iodide and sodium chloride as the salt mixture in here. That's the molten salt. Here is the cathode. So that's where the sodium gets deposited on the molybdenum, and then graphite rod is where the gold gets deposited. You have the thermocouple to control the temperature and all of the wires for voltage and current control. So before the anodic deposition, they took graphite, they immersed it in the salt for 2 hours to ensure that there is no chemical deposition that's happening. So they wanted to see if there's any cationic species of gold that gets reduced based on the presence of sodium. So it's similar to the corrosion. They wanted to make sure that whether there's any electroless deposition that happens, and they did this for 2 hours, and they didn't see any gold at all. Here's the cyclic voltammetry they did. This is before they added gold and sodium. They did a bare CV as well as with the gold and sodium. So basically, as you went cathodic, you deposited sodium, and then you came back. This is similar to our hydrogen adsorption and desorption CV. In this case, it's a sodium in the molten salt. And as you went up, since there is no gold present, this is blank, they were releasing iodine gas. There's no oxidation peak. But in the presence of gold, this is how they see the CV. Okay, so pure molten salt without any sodium or gold added, and then with the sodium and gold added, this is the peak that they saw. So when you are going cathodic, there are two reactions that are happening. So you're depositing sodium, and then you're also going from gold, which is metallic, into anionic species. So this is a mixed reaction that's happening here. When you're going anodic, you're oxidizing and you're depositing gold. This is how they're confirming that they are depositing gold on this. This is the previous one is the CV, and you always have this mixed reactions on this side and then oxidation on this side. They just picked one voltage and then stayed there for a long time to understand how much gold they are able to deposit. So they did that, potential static, and they deposited gold here. And they did SEM and EDS. Here's the peak for gold, point B. Here's the point at which they confirmed the presence of gold. They also did X-ray diffraction. Here's the X-ray diffraction where they compared it with the standard gold versus what they got as a sample. Okay, stop share. That's the paper, and we can discuss now.
Okay, yeah. One thing that was interesting for me, so in school last year, I took chemistry, and then we basically had to do this project where you choose anything like related to chemistry outside that can be done as an experiment from home. So I'm gonna send a link in the chat. Basically, I found like when I was doing research for this, it was like an Instructables like with a process for how to get gold from like old devices. So basically, they said you can use like HCl, and like from like an etching solution, and yeah, it's just 9.5 peroxide and HCl, and then that would just like get you gold foil, which you can just keep as a decoration. Of course, it's not like the same as like this. This is for pure gold, but I just thought it was interesting, like the connections between that.
True, nice. Thanks for sharing. Yeah, that's very nice.
I had a question or a comment.
Yeah.
I don't really know. I've never what we do for platinum for fuel cells. I don't know if that is the same way or the electrochemistry could be similar, where you can go from or it is aqueous solution enough that this solubility wise, you can do it from easier chemistry than going to molten.
Good question. I haven't done.
Yeah.
I think they follow hydrometallurgy process similar to the current process. Even for similarly lithium hydrometallurgy is what they're using for lithium recycling as well. All of this is temperature, pressure, and solvent chemically.
And how you alloy it and how you separate it later.
Correct, exactly. But yeah, good thing to. It'll be good to look at platinum and see if there's a similar process possible there.
Yeah, I'll look into it.
Ayyappan, you are on mute if you're talking.
Okay. Yeah, did they mention, I mean, like they did only like 2 cycles, right? In the CV, if I...
Correct.
Okay. And then the initial peak of their oxidation peak was very small compared to their reduction peak. Right. And they haven't mentioned anything about, is it because they just started close to the OCV? That's why the peak intensity is very small. Is that could be?
Yeah, they didn't go into the details.
Oh, okay. Details of that CV. Okay.
Correct. Other thoughts, comments, questions? So my thought process was certainly because it's brand new. I think they just did the minimum work and then published. There's only cyclic voltammetry and this one potential static run, and then couple of SEM and then XRD. Not a detailed, comprehensive studies like the other papers. Mm-hmm. As you can see, in 20 minutes, we completed discussion of this paper. Mm-hmm. So basically, they started with gold and sodium from, they created the alloy rather than using the actual PCBs.
Okay.
So what's not known is all the interferences that may happen in a real system.
PCB. Mm-hmm.
So when you look at their experimental setup, they just started with sodium and gold and from raw material and then alloyed it and then created a test system. So that's one thing that I saw. I think it would have been nice to include other components. Even if they wanted to simulate the system, they could have added other metals that were expected as part of the alloy and then material, and then they could have started that.
Yeah, that's what I was about to ask. Like, how did they process their PCB boards to get their starting material? But that's they did an alloy homemade.
Correct, okay. Correct. One thing I think takeaway, maybe as we move forward in these literature review sessions, we can have an experimental procedure as well as a slide for us to go through.
Sure.
So we can start doing that.
Yeah, I think them not creating their own or them not using PCBs and instead creating their own goes back to like what you were saying is kind of like a rush. They just wanted to publish like the bare minimum. So, but like maybe if in like a second paper, like after they have more time, then they're gonna actually use real PCBs or simulate it better.
Correct. Yeah.
How do they remove the gold from the rod after that?
So it's just they didn't. Probably, I don't know. They don't. I don't remember.
I'm just
talking about. Yeah, we can bring up the paper, or you
can, I have the paper, and I'm trying to find if they say anything about that. It doesn't look like, because once I have that, I have the purity on the carbon. I can burn it off.
It's possible because they do have a picture of gold separated out.
Yeah, I know.
Yeah.
Somebody showed, but how did they do it?
Yeah.
It doesn't look like powder. It looks like some kind of like shape that they deposited. It kind of came in that circular rod shape. Yeah.
Oh, was it inside? Was there a hollow? It looks very thin compared. Oh.
They just say rod. I don't know if it's a solid or hollow.
Yeah. It doesn't like it. It looks like that will be interesting to see if it just comes off or doesn't stick. Then it will be powder.
Yeah.
I don't know how they treat it. I mean, obviously they're showing the rod and the gold, so obviously they didn't burn it off. They didn't burn the carbon. So
my thinking is, if the CTE is different enough, even if you slightly heat it up,
it'll come off. Maybe.
It'll come off.
Yep.
So I don't know.
It'll come off because it's coated around. It'll come off as powder.
Come off as a cylinder, right?
Will it come off? Okay.
Yeah, because it's all the gold is connected.
Yeah, sure. You're right. Yeah, and then it'll come up. It'll open up and come off as a as a volumetric.
Yeah, I think it's a groundbreaking, brand new approach. So they wanted to get it out, and lots of discussion on how gold had been dissolved as an anionic species in the solution, like 2 or 3 paragraphs on that, on how various groups just dissolved it. That's it. Dissolution.
When you see when we go through electrochemistry, cathodic reduction, that's where plating happens.
Correct.
The fundamental shift in that.
Correct. Yeah. Okay. Any other comments? If not, let me share screen again, and then I'll say what we are going to be discussing next week. So next week, the paper is going to be on flow batteries. Ayyappan will be leading the discussion. And then again, any of you are welcome to join as a lead. If you are interested, please send an email to info@vetrilabs.com. With that, we can stop the recording session for today.